Hello calculus students. Welcome to the series of videos on optimization problems. And optimization basically means to find the best answer. The word best though changes from situation to situation. So this is really an exercise more so in problem solving than it is in calculus. There's some calculus involved in here though, of course. So let's start out with the first problem. A man launches his boat from point A on a bank of a straight river, 3 kilometers wide, and wants to reach point B down here, 8 kilometers downstream on the opposite bank as quickly as possible. He can row 6 kilometers per hour. That's pretty good. And run 8 kilometers per hour. So where should he land to reach B as soon as possible? Well, we can think of this before we actually attack the problem. We can think of this as two extremes, okay? So look at the extreme scenarios. In the first extreme, he could just row as much as possible. So row as much as possible. In other words, he could go directly from A to B. Okay. So that distance is, since this is 3 and this is 8, this distance here is the square root of 8 squared plus 3 squared, or the square root of 73. So he is going to row root 73 kilometers at a rate of 6 kilometers per hour. So 6 kilometers per 1 hour, in which case it will take him root 73 over 6, which is approximately equal to 1.42 hours. Okay. Then the other extreme, 2, is that he could row as little as possible. So he's going to go directly from A to C. He's going to row this distance, and then he's going to run this distance. Okay. So the total time that it takes him is going to be, well, he is going to row a distance of 3 kilometers from one side of the river to the other. That's that distance. At a rate of 6 kilometers per hour. Plus, he's going to run 8 kilometers at a rate of 8 kilometers per hour. So altogether, that's going to take him half plus 1, or 1.5 hours. Okay. 1.5 hours. So you can see that given the two extremes, this one's a little bit better than this one. Okay. But that's not the best answer. That isn't the optimized solution. So let's look at what is the optimized solution here. And to do this, what we really need to do is create a function . T of D, where D represents the distance from point D. Okay. So in other words, from point C. So in other words, the best solution is probably for him to take some type of path like this, to row to here and maybe run the rest of the way. Okay. To row to here and run the rest of the way. And this distance right here, we can call that D. And then he's going to run the entirety of the way. Okay. And then we're going to find D such that T of D is a minimum. Okay. And so what we're really saying here is that T of D represents the total travel time. And now comes the harder part of the problem. So we're going to write this function t of d, but if you notice right here in this picture, we have a good solid Pythagorean theorem, or a right triangle where the Pythagorean theorem can apply. So this distance here is 3, and this distance here is d. This hypotenuse is how far he's going to row. So the rowing distance. And then this length down here is how far he's going to run. Okay. So in other words, he's going to run this length, which is the square root of 3 squared plus d squared. And he's going to run this length, which is 8 minus d. So this length here, whatever it is, it's going to be 8 minus d. Right. So now we can set up this equation quite nicely. The total time that he takes is going to equal how far he has to row. I'll just make this a 9, times the rowing speed, or really divided by the rowing speed, 1 over 6, plus how far he has to run, which is 8 minus d, times, or 1 over the running speed. Okay. So think about what all these numbers mean. This is really critical to understand what these numbers mean. This is the row distance. This is the reciprocal of the row speed. This is the running distance. And this is the reciprocal of the running speed. And once we have this t here represents the total time that he has. So now, if you notice here, we haven't actually done any calculus yet. This is all algebra and maybe a little bit of geometry. And all we really have to do is take the derivative and use what we know about the first derivative test to find the minimum values. So now we can take the derivative. Let's see, t prime. I'm going to pause here so that you can try and do this on your own. Alright, so that's what I got for the derivative. So I made this is really 9 plus d squared to the 1/2. Applying the power rule, get the 1/2 and the negative 1/2 right here, times the derivative of the inside function, which is 2d, and then times this 1/6. Over here, if I distribute the 1/8, I really have 1 minus d over 8. So the derivative of 1 is 0, and the derivative of minus d over 8 is negative 1/8. And this is the derivative. I'm not sure exactly what it means, and we don't really care about that too much in this particular problem. We really are only interested in using the derivative to find the minimum. So to do that, we got to find the critical points by setting this whole thing equal to 0. And then in this step, I'm actually going to simplify. So this 1/2 and the 2 will cancel each other out. So I'm going to and then this is really 1 over the square root of. So this is 1 over 6 times the square root of 9 plus d squared minus 1/8. Okay. So we can move 1/8 to this side. Multiply both sides by the denominator and multiply the other side by 8. So we get 6 root d plus, or 9 plus d squared equals 8. Divide both sides by, or I guess we could square both sides, so we get 36 times 9 plus d squared is equal to 64. Divide both sides by 36 and then subtract 9. Oh, wait a minute. I made a bad mistake here. I forgot to use this D right here. So somewhere when I simplify from here to here, I lost that D. So that was a problem. So this should say D, and if you multiply, this should be 8D. So this is 64D. Squared. Okay. So we get something a little bit different. So what we get here is 144 plus 36D squared is equal to 64D squared. 144 is equal to 64 minus 36, which is 28. D squared, 144 over 28 will give us 36 over 7, and that means D is equal to 6 over root 7. So in other words, what we want to do, let's think about what this D actually means. Okay. Well, remember that D represents the distance from point C to the point on the shore. So if we were to row to a point that is 6 root 7, which is about 2.267 kilometers, if we were to row to a point around here where this red length here was 6 root 7, then that would be the point where we could minimize our time. Okay. Now, one thing that I didn't, I kind of glossed over here was that we really needed to check for sure, to be sure that this point is in fact the minimum, but it really is. This is the only minimum that's going to exist in this particular function. Okay. So there we go. This is a introduction to optimization, and as you can see, one problem can be quite involved, and this one has taken us quite a while, mostly because I wanted to introduce some extremes here just so that we can use and compare. And in fact, if we were to take 6 over root 7 and plug it back into this function, we'll be able to distinguish and see that the result is in fact smaller than either one of these numbers. Okay. And here we actually don't care what the time actually is, other than to check our answer. We just care that the point where we need to row to is in fact equal to D. Okay. The first time that you do this, it can be overwhelming, which is why we're going to do many of these problems. Remember to keep working at it, and as always, ask for help. Have a wonderful day. Make sure you watch the next video.